Hi everyone, welcome to the PCD of Codechef Starters 173. I am Pradyumn Kejriwal and this is TLE Eliminators. Today we'll discuss the first six problems of Division 1. Actually today all four divisions have the same problem set. So we'll discuss the first six problems. Also, before getting started, I would like to tell you about the TLE's CP31 sheet. So this is a problem set curated by experts and CMs on code forces which have like the best 31 problems of every rating from 800 to 1900. And if you solve these problems, then mostly you would be able to like cover many topics of these ratings. And a good feature of this sheet is that you can like link your CF account and it will show that how many problems you have already solved. And also we will be releasing YouTube video solutions of these problems. All right. So let's get started. So first we'll discuss the first problem, which is time penalty. You are participating in Codechef Starters 173, which has a time penalty of 10 minutes for every incorrect submission you make. That is, the total penalty of a problem equals number of minutes from the start till your submission plus 10 minutes for every incorrect submission you made. You solved the problem X minutes after the start of contest and made Y incorrect submissions. What is the total time penalty of this problem? So I think this is a quite an easy problem. Like we just have to take the input and print the output. Like basically the problem is like we have solved X minutes later and Y incorrect submissions we have made, right? And for each incorrect submission, we get 10 minutes penalty. So the final answer would be like 10 into Y plus X, right? So that is very simple, that we have to just take the input of X and Y and print 10Y plus X. All right. So I think that is clear. I'll just show you the code real quick. So I just take the input and print X plus Y into 10. Okay. So I hope there is no doubt in this. Like if anyone has a doubt in this, then they can ask. I am counting till 5. Okay. So 5, 4, 3, 2, and 1. So I'm assuming that no one has a doubt in this. Okay. So let's move on to the next problem, which is called cool subsequences. You are given an array A containing n positive integers. A subsequence of this array is called cool if the averages of all non-empty subsequences of the subsequence are present in the complement subsequence. The complement subsequence refers to the subsequence formed by elements we didn't consider. For example, consider the array A. Consider subsequence 2 to 8 of this array. So 2, 2, and 8. Okay. The complement subsequence is 841, 352. So the elements that we didn't consider from this, the non-empty subsequences of 2 to 8 are all these 7 subsequences. I mean, some are repeated, so maybe they haven't written them, but they are the subsequences with averages of 285, 282, 5, and 4 respectively. So like the average is 2, average is 8, average 2, 5, and 4, right? All of these values are present in the complement subsequence, that is this subsequence, right? So that's why 2 to 8 is a cool subsequence. Okay. So, and there is no rounding done when computing the average, right? Find any cool subsequence of the array with length at least 1 or report that no subsequence exists. So, okay. The problem goes like there is an array that we have been given, right? And we have to just report a cool subsequence. And a cool subsequence means that, like, let's say, I'll take this example only, that let's say 2 to 8. So 2 to 8 is a subsequence and it is cool because averages of all non-empty subsequences of this subsequence, like 2 to 8 is an array, and if you just check all subsequences of this 2 to 8, then you will get 2 8 2 2 2 8 and 2 to 8. So all of these averages are present in this complement subsequence. Like if the in this array, if we consider 2 to 8 as a subsequence, then the complement is this one, right? So that's why um, all of the averages all of these averages are present in this complement subsequence, and that's why the subsequence is cool subsequence. And we have to just print any cool subsequence of length at least one, right? So let's think about it. So actually, what if we just print a subsequence with length one? Like, let's think about that. Basically, what I am trying to do is, let's say we have an array 1 2 3. Now if I tell you that 1 comma 2 is cool, like hypothetically, let's just say 1 comma 2 is cool, or let's get a better example. I'll take the one from this only, that 8421 8421 32582. Okay. So in the statement, they are saying that this 2 to 8 is a good subsequence or cool subsequence, right? 2 to 8 is a cool subsequence. So what do we know? That all of the averages of subsequence of this subsequence are present in the complement. So this 2 we have taken, this 2 we have taken, and this 8 we have taken. So all the remaining elements are the elements which are the average, like, right? So like the averages are um, 2 8 2 5 and 4, so they are present. 2 8 2 5 and 4, they are present in the complement subsequence, so we can say that. But now if I ask you that, okay, one subsequence of this array is 2, right? So definitely we want that 2 exists in the complement subsequence. And since this subsequence is cool, then that means that 2 exists in the complement subsequence, right? So what does that mean? That um, since this is good, like since this is cool, 2 exists in the complement subsequence. So what can I say? That this is also cool, right? This one is also cool, because the subsequence of this is what? Just 2. Like there's only one subsequence of this array, which is just 2, and the average of this is 2. And since we know that 2 exists in the complement subarray, so this is also a cool subarray or subsequence. Sorry. So what I'm saying is, if we have a cool subsequence of length greater than 1, then definitely its subsequences will also be cool, right? So we can just find a subsequence of length 1. Okay. So if it is not clear up till here for anyone, then please let me know. Like if I repeat myself, what I'm saying is, if that this 2 to 8 is cool, right? So that means that 2 individually and 8 also individually, they are cool, right? That's what I'm saying. So is it understood by all? Just write a yes in the chat if it is understood. Yes. So basically, if a longer subsequence exists, like this 2 to 8 is cool, then this 2 is also cool. So what we can just do is, we can just find a subsequence of length 1, which is cool. Okay. So let's say we have been given an array 1 2 3 3, right? So let's say that I want a subsequence of length 1. So what if I take this 2 as my subsequence? So is this cool? Is this cool or not? It is actually not cool, because the complement subsequence is 1 3 3. and the average of its subsequences. So what are subsequences of this? It is just one, just two, and the average of that is two, which is not there in this complement sequence. So that's why we cannot, this two is not there. But what we can do is we can take three. We can take three as subsequence. So what is the complement of this? Complement of this is 1, 2, and 3. And what all subsequences are possible from this? Just one, right? Just three. And the average of that is present in this array. So therefore, this 3 is actually a cool subsequence. Okay. So that's my point, that we are able to find a subsequence of length 1, which is cool, right? So that is that whichever element has frequency greater than 1, like since 3 occurs 2 times, we can just take one of the 3 as our subsequence, and we'll find the average in the complement. The other 3 will be there in the complement subsequence. Okay. So what we can just do is we can just iterate over the array and count the frequency of each element. And if each element, like if any one of them occurs more than once, then we can say that um, like we can just take that element. We can just take that element and the subsequence will be cool. All right. So that's my point. And if there are no distinct elements, I mean, if there are no duplicate elements, then what will we do? Let's say the array is like 1, 2, 3, 4. Then what do we do? Then actually it means that there is no cool subsequence. Why? Because let's say I take any element. I take 2. Then the complement is 1, 3, 4. And the average of 2, which is 2, is not in this subsequence. So if I take any number, any singular number, the complement of that won't exist. The average of that won't exist in the complement if they are not repeated. So that's why the answer is -1 in that case. Okay. So I hope it is clear that you can just take any duplicate element and it will form a good subsequence, a cool subsequence, right? So is it clear, guys? Or any doubt you are having? That in the entire array, just take a duplicate element, like this 3 in here. So for example, in the test cases, sample test cases, we can take just 2. Like if this is the array, then we can just take 2, and that is cool. And in this array, there are no duplicate elements, so the answer is -1. So is it clear, guys, everyone? Okay, I hope it is clear. So I'll just show you the code that I'm just counting the frequency of each element by using a map. Okay. So yes, this is the code that int n c in n, and I take the input of n, map of ll comma ll fr, and I just increase the frequency for each element in the array. Now for auto x in fr, that means for every pair, if x dot second, that is the frequency of x dot first, if it is greater than 1, then I just print x dot first. And also it demands the size of the array as well. So I just print 1 and then x dot first, and then I return. And like if this condition is not satisfied for any x, then print -1, because all the elements are distinct. Okay. So is it clear, guys? Okay, I hope it is clear. So I'll move on to the next one. Okay. So the next one is called overwrite. You are given two arrays A and B of lengths n and m respectively, where m is less than equal to n. All the elements of A are distinct and all the elements of B are distinct. Okay. In one operation, you can do the following. Choose a subarray of A with length m and replace it with cyclic rotation of the array B. For example, if A is equal to 2, 3, 3 to 5, 4, 6 and B is 2, 1, 3, then you can choose to replace the subarray, this one, with the array 3, 2, 1, which is a cyclic shift of B to obtain 3, 3, 2, 1, 6. Okay, so this is the operation that we can do. Like we have been given two arrays. Let's say array A is this. This is the array A and this is the array B. Let's say 1, 2, 3. Then we can do this. We can just choose any subarray of A of size 3 and replace it with B. Not just B, we can replace it with any cyclic rotation of B. So 1, 2, 3 or 3, 1, 2 or 2, 3, 1. So any three of these we can put here instead of this original A. All right. Your task is to find the lexicographically minimum possible array A that can be obtained by performing this operation several or possibly 0 times. An array P of length is lexicographically smaller. Okay, so lexicographically definition they have given us, and I think most of all of us know that what is lexicographically smaller. So yeah, so our task is that we have been given two arrays and we have to like do this operation once or like any number of times to this array A to make it lexicographically minimum, like the minimum lexicographically, right? So how will we proceed? Let's look at the sample test cases first. Okay, so I'll first look at this one, 1, 2, 3, 4 and 5, 3. So array A is 1, 2, 3, 4 and array B is 5, 3, right? So what are the cyclic shifts of B? It is either 5, 3 or 3, 5, right? So we can choose any subarray of length 2 in A and replace it with either 5, 3 or 3, 5, right? So now we have 1, 2, 3, 4, right? Now what we can do is we want to minimize this, right? Lexicographically. So what we can actually do is we can iterate from left to right. So initially when we had 1, 2, 3 and 4. So if we iterate, first of all, we want to make this minimum. Okay. Like this index, I have to make minimum. So initially it is 1, right? So can I make it less than 1 using just 3 and 5? No, right? I cannot make it less than 1 because if I apply either 3 or 5, 3, 5 here or 5, 3 here, uh, either 5 or 3 will end up here, right? So I cannot make it less than 1. So I'll just keep it as it is. Okay. So I'll just keep this one as it is, right? Now I come to 2. So I cannot make it less than 2, right? So I'll still keep it as it is. Now I come to this 3. Okay. So like in this 3, we can see that if I replace it with 3 comma 5, then what will happen? This array will become 1, 2, 3 and 5. But this is actually greater than 1, 2, 3, 4 because 5 is greater than 4, right? So we won't do that. So basically the final array actually remains 1, 2, 3 and 4 in this sample test case. We don't do the operation at all. So the answer is this. And let's see the another test case, 2, 3, 7, 1 and 4, 3, 6. Okay. So what we can see is here. So 4, 3, 6, what we can we can replace either with 4, 3, 6 or we can replace with 3, 6, 4 or we can replace with um 6, 4, 3, right? So these three uh, operations we can do on this array. So the array is 2, 3, 7, 1. Okay, so now if you see that we actually cannot like we cannot make it less than 2 because the minimum element is 3. So even if we perform the operation here, this element can become 3. It cannot become less than 2, right? So we won't perform it here. Now if you look here, we have 3. So if we perform with 364 right here, so if we make it 364, then the array will become 2364. And this is actually less than 2371, right? So therefore, this is the answer, 2364, right? Now actually these samples are pretty weak, so I'll show you another test case that I have made, like sort of. So let's say we have A as 5, 6, 7, and 8, and B we have 2, 1. Okay. So in this case, what we can do, we can either replace with 2, 1 or 1, 2, right? And actually we want to minimize, right? We want to minimize A. So definitely we will replace it with 1, 2 because 1 is smaller than 2. So basically, if I have two options, that either I have like x, y, 1, 2, or I have x, y, 2, 1, then obviously I would prefer 1, 2 in any case because I want to minimize this. So definitely I will always replace with 1, 2. Now if you see, if I put this 1, 2 here, okay, I'll just write it again, 5, 6, 7, 8. If I put this 1, 2 on the first index, then actually this element will become 1, right? So that's why I will put 1, 2 here. Okay. So I'll put 1, 2 here, right? Now, now you see that this thing has become 2. But actually I can make it 1 also, right? By just putting 1, 2 here. So I'll do that. So I'll put 1, 2 here. Uh, wait. Okay. So I'll put 1, 2 here. And again, here you can see that this 2 I can reduce to 1. So I'll again put 1, 2 here. Somehow this is not working. I'll just troubleshoot that. Okay. Now it is working. Yeah. So um, if I put 1, 2 here, now what I'll do, I'll put 1, 2 here. Okay. So the final array becomes like this. So actually, after seeing this test case, you might get some idea about how to proceed, right? Because it is given that the X, A and B arrays have distinct elements, all distinct elements. And I have told you that definitely you would take the minimum element on the front, right? So let's say you have some array 312. Let's say B is 312. Then what you'll actually do is you will start with this 1. Like you will try to keep this 1 at the front. So you will actually do 1, 2, 3, right? And once you do that, let's say you have an array A. This is the array A originally, okay. And then you choose an index. You at this index, you apply 1, 2, 3, okay. So you applied 1, 2, 3. Now, irrespective of what was there before at this index, now it is 2, right? Now it is 2. So definitely you will apply again 1, 2, 3 because 1 is the minimum element. So therefore, this element is definitely greater than 1. So you will definitely apply 1, 2, 3 again here. So what will it become? It would become 1, 2, 3 like this. And now here also 2 has come. So again you'll apply 1, 2, 3. So it has become 1, 2, and 3. And now you can stop because you cannot apply it here, because you need to select at length, like subarray of length 3, right? So in general, you can easily see that what I can just do is I can cyclically shift the array B so that the minimum element is at the front. Like for example, if I say I have 4, 9, 8, and 12, and maybe 3. Okay. So what I will do is 3 is the minimum element. So I'll shift it. I'll cyclically shift this array and make 3 come to the front. So 3, 4, 9, 8, and 12. So now I can apply this to my array. Okay. So let's say this is my array A. Now let's say there is some 1 here, 2 here, 1 here, 4 here, 5 here, 6 here, 2 here, 1 here, and 8 here. Okay. Now I want to minimize this, right? So I'll start with the first index. This is 1. So definitely I won't apply this array because it will become 3. Okay. Now this is 2. So I definitely won't apply it here also. This is 1. So I won't apply this here. But this is now 4. Okay. So if I apply this here, if I apply this array of length 5 here, then this would become 3. So I'll apply that here. Okay. But if I apply that here, 3, 4, 9, 8, 12. Okay. And these elements are gone. So now if you see, 3 is right here. But after this 3, like at the second element, definitely it is something greater than 3. Right? Because B has all distinct elements. And since B has all distinct elements and 3 is the minimum element, then after this is definitely something greater than 3. So we will definitely apply it, we'll definitely keep applying the operations as we can. So we'll definitely apply it again. So we'll apply 3, 4, 9, 8, and 12. And these numbers get erased. And this 8 also get erased. Right? So finally the answer becomes like 1, 2, 1, 3, 3, 4, 9, 8, and 12. Right? Or if I take one more example, let's say we have 3, 4, 5 as B. Okay. And our A is initially, let's say 10, 10, 10, 10, 10, 10, 10. Okay. Or let's say 10 and 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. Sorry, A can't have duplicates. That's right. So I'll just erase this and I'll make it like 10, 1, 2, 3, 4, 5, 6, 7. Okay. So now if I apply B on this index, if I apply B, then it will become 3, 4, 5. Okay. So 3, 4, 5. Now I'll definitely apply here because it is 3. So actually, can you just predict that what will happen? It will actually become like this only: 3, 3, 3, 3, 3, 3, and then 4, 5. Right? You can just do that in one go because you know that definitely this 4 is greater than 3. So when you apply this 3 to this index, then the next number is definitely greater than 3. So you'll definitely apply there as well. So you'll keep applying. You will keep applying this and the chain reaction will happen. And at the end, you will apply at the n minus mth index. Index n minus m. So it will be like 3, 4, 5. So it is like you find the first index where this 3 is greater than the array A element, right? So here you had found 4. So you replaced it with 3 and then a chain reaction followed where you kept applying. So that will happen. That will happen except the case where m equals 1. Like if the length of B is 1, let's say B is just 2, for example, then then the case is trivial. Like then you can just do something like traverse over the array A. Let's say we have 3, 1, 2, and 4, and let's say 5. Then basically you will just replace whatever the elements are greater than 2 with 2. So you will replace 3 with 2, then 1, 2, and then you replace 4 with 2, and 5 is also 2. So this is the case of when this is the case when the length of B is 1. You just replace all of the numbers greater than 2 with 2. But if the length of B is not 1, then if you are applying at some index, so like you will find the first index which is greater than the smallest element in B. Okay, so first of all, you will cyclically shift the B, right? So first of all, if it is 5, 4, 3, then you will make it 3, 5, 4. And then in the array A, you will find the first element that is greater than 3, right? So let's say that is here. Then you will apply 3, 5, 4 right here. Or let's say it is here. Let's say there was 4 here. So you applied 3. Like you applied 3, 5, 4, and a chain reaction will happen. So you will apply 3 here, and then 5, 4. So that's how you make the array A. But what if you don't apply at all? Like, what if you don't apply this operation at any index? So let's say the array B is something like 8, 9, 10, and array A is something like 1, 2, 3, 4, 5, 8, 10, and 11. Or let's just keep it simple right now, and 6, 7. Okay. So if you don't apply, like, okay, so 1, 2, 3, the minimum element is 8. So all of the element 1, 2, 3, 4, 5, 6, 7, they are all less than 8. So definitely you won't apply this operation. But actually, let's say that here instead of 5, 6, 7, it was something else. Let's say we had 1, 2, 3, 4, 8, 12, and 13. So here, actually the second last index, I mean the third last index, this is actually equal to 8, right? So if we apply this 8, 9, 10 here, then the array becomes smaller, right? So in that case, this is the answer. Like basically, if we are not applying this, like if we cannot find any index where the element of A is greater than 8, then we have to just check that if we apply at the last, then is it less than the array or not, right? So in this case, if you apply, then it would be like 1, 2, 3, 4, 8, 9, 10, which is like greater than this array. But if you apply in this array, like if this was your A, then this answer is actually lesser than this array. So you basically just need to check that if you apply it last, then what will happen. So two cases are there, that if you found any index where the element of A is greater than the minimum element in B, then the chain reaction happens, and this 3, 3, 3, this fills up. And otherwise, you can just check that the end in, like if you apply this 8, 9, 10 at the end, then is it lesser or greater? So that's what I did. Okay. So everyone, do you get it? Basically, if the m index is equal to m, just check if which one is smaller. Yes, just check. Like just apply and check out of both of those that which one is smaller. And actually in C++, if you use vectors, then by default you can just use min and it would compare by itself. I'll show you the code. Like, but before that, do you have any doubt? And yeah, if m index is equal to m, then check. But actually you don't need to check if you have already applied before. Like let's say in this case here, instead of 3 it was something like 10. Okay, then actually you would apply 8, 9, 10 here, right? And the chain reaction would follow. So 8, 8, 8, and then 9, 10. So if you haven't done that, then only you need to check that, okay, is the last three elements, is it beneficial to apply, right? Okay. So I hope it is clear till now, and I'll just show you the code. Okay. All right. So I took the input nm c in nm vector of int c. So actually this c is to store the cyclic shift of b. Like basically what I'm doing is I'm bringing the minimum element of b to the front and storing that entire array in c. Okay. So I took the input of a and took the input of b. And yeah, this is the edge case here, that if m is equal to 1, then just replace ai with min of ai comma b naught. Like just replace all of the elements that are greater than b naught with b naught, and then just print the array. Okay, so this is the edge case, and I handled right here. Now I am just constructing the cyclic shift of b. So c dot pushback b of min index plus I mod m. So this actually does cyclic shift. So like I use this function min element to find the index of the minimum element in the array b. Okay. So this C now contains the cyclic shift of the array B. Okay. Now I just iterate through the array A. So I go from I equal to 0 to n minus m plus 1, like n minus m, because that is the last index on which I can apply. So if AI is greater than C0, which is the minimum element, C is the minimum element, then flag equals true. Flag equals true means that I have applied the operation. And basically from that index, like from that I to n minus m, I just set it to C0, right? The chain reaction. And after that, I just set it to CJ. Like I'll just apply at the end. So if I show you from here, it is basically doing something like, suppose it is 8, 9, 10, 11, and 12, and B is something like 2, comma 3. Then it found this element greater here. So it is putting 2 here. Then it is putting 2, it is putting 2, it is putting 2, and then it is putting at the end 3. So that's what it is doing. That up till the index n minus m, I just put c naught, that is 2, and after that I just put the array c. All right. So that's what I will do. And if flag, then break. So if I found an element which is less than the minimum, then I break. Also greater than the minimum, then I break. And if flag, which means that I did the operation, then I just print the array. And otherwise means that I never did the operation. So I just need to check that, okay, if I apply the element, like if I apply the array C at the end of the array A, then will it benefit me or not? So I just made these two vectors. Like A1 is just A, like initially what was the input A, that is just A1. So for int I equal to 0, I less than I plus plus, I just push back A1 into, like A into A1. So this A1 is just A, and this A2 is like when I what I applied after, like I applied C at the end. So first n minus m characters would be from A1, like from the initial input A, and the last m characters would be the C array. So this A2 is the applied, like when I apply C at the end, and ans is equal to min of A1 comma A2, the smaller one. So I just printed the ans. Okay, and you can actually do this, like A1 and A2 are two vectors. So by default C++ just compares them in lexicographical order. Okay, so yeah, that's it. That's the code. So I hope it is clear for everyone. Is the code clear, everyone? Clear. All right. So I'll move on to the next one. So the fourth one is introverts. Okay. There are n empty seats in a row, numbered from 1 to n. N introverts arrive one by one in order from 1 to n and choose a seat for themselves. Being introverts, they have some rules to minimize contact with other people. Primary goal, the person will aim to maximize their chosen seat's distance from the closest occupied seat. Okay, so whatever, so basically, let's say there are some seats, there are n seats, okay, and let's say in these two seats, people have already sit. So what will the introvert do? Like introvert will actually come and either pick this seat or this seat because it is the farthest from any chosen seat. Like it gives distance 2. All the other seats give a distance of 1. Like this seat is adjacent to this one is adjacent to this thing, right? So that's what will happen. Like either he will sit here or here. Okay. So that is the primary goal. And secondary goal is that in case there are multiple seats satisfying the primary goal, the person will aim to choose a seat such that the next person to arrive will have a higher distance from the closest occupied seat. That is, the person aims to help the next person meet their primary goal better. So basically, what they are trying to say is, let's say in this example, these two seats have the same minimum distance that is of 2, right? So, how will the person choose? They will actually choose the one for which the next person who will come have a better chance. Like, let's say right now, someone comes and sits here, okay? Then the next one who will come has a minimum distance of 1. Like, all of these four indices, this one, this one, this one, and this one, all of these four seats have a distance of 1 from the occupied seat. So if I sit here, then the next person will have a distance of 1. But if I sit here? If I sit here, then also the next person will have a distance of 1 only. So basically these two seats are equivalent. This one and this one are equivalent and I can sit in any one of them. Okay. So that's what it happens. In case multiple seats satisfy both the goals, ties are broken arbitrarily, which means that I can sit anywhere, wherever I want. All right. So now, formally, okay, so they have given the formal definition. We don't need that because we understood what they want to say. If we denote pi to be the number of the person sitting in seat number I, then p1 to pn is a permutation, right? So basically, they are saying that the first person, let's say he sat here, then second one sat here, third one sat here, fourth, fifth. Actually, okay. So let's say the first one sat here, second sat here, third will sit here, fourth, fifth, sixth, and seventh. So this is the final arrangement, and it is a permutation, right? So that's what they are saying. Given a permutation P of the integers from 1 to n, determine if it is possible for n introverts to seat themselves according to the above rules such that their final arrangement forms the permutation P. Okay. So the question is like they have given us the final arrangement. So like this is the final arrangement, and we have to determine that is it possible that the introverts sit in this order? Like, is it possible that the introverts sit like this? Okay. So that is the question here. Just 1 minute. Okay, is my screen visible? All right. Yeah, so the question is like this. Okay. So actually, let's understand that the primary and secondary goals better. Okay, let's understand them. So the primary goal is to maximize the distance from the closest occupied seat. So what does that mean? That let's say I have a person sitting here, then I have some blank space, then a person sitting here, then some blank space, and a person sitting here. Okay. So either the next introvert who comes can either sit in this blank space or in this blank space. Actually, this is not just one blank space. It is a series of blank seats. Okay. So it's like kind of like this. Person sitting here, and then many seats, then a person sitting here, and then many seats, and then a person sitting here. So basically the introvert who comes either will sit in this one or this one, right? So actually he'll try to sit the farthest from any close, right? So he'll try to sit in the middle, like this gap and this gap. So either he'll sit here or here, but wherever he sits, he'll try to sit in the middle, right? Because let's say he sits here, then the distance is 3. But if he sits not in the middle, like if he sits here, then the distance is reduced. So obviously he'll try to like sit in the middle of the distances, right? So that's one thing to observe. So let's say we have something like this: person sitting here, 1 2 3 4 5 6 and 7. Person sitting here, 1 2 3 4 5, and then here. So where will the next person go? Obviously he will go here, right? Because this center gives distance of 4, right? If he had sit in this center, then the distance is just 3, right? So that's why the person will try to sit here. Okay. So in general, if I want to say, in general, if there are some x people between, there are some x seats between two people. Let's say there's one person here and one person here, and there are x seats. Then basically, if I sit in the middle, then what's my distance? And what is my distance? Let's calculate that. Okay. So for two, let's say what is it? So if there are two gaps, then the distance is what? Uh, Either I here or here. So in both the cases, distance is 1, right? So for 2, it is 1. What if for 3? For 3, if I sit here, the distance is 2, right? So for 3, it is actually 2. For 4, 2, 3, 4. For 4, it is if I sit here, then the distance is 1. Yeah, here also distance is 1. Sorry, distance is 2, right? So for 4, the distance is 2. And for 5, 3, 4, 5, the distance is actually 3. So as you can see that the distance is actually half the length, like approximately x by 2, not exactly. So basically, if we observe the pattern from here, for 2 it is 1, for 3 it is 2, for 4 it is 2, for 5 it is 3, for 6 it is also 3. So we can actually say that it is the ceiling of x by 2, the ceiling function of x by 2. That is the distance. Okay. So if we sit in a gap of x, then we can have x by 2 distance, the ceiling of x by 2 distance, right? So let's say a person came. So let's say there were two gaps. One gap was of 5. 1 2 3 4 5, and one gap was of 6. 1 2 3 4, 5, 6. And the person chose the center of this 5. Person sat here. So is there any contradiction in this? Like, is the person violating any rules? No. Yeah, because in both the cases, if you see that in both the cases, the distance is just 2. Like here, the distance is 2. And if I had actually sitting here, if I sat here, then also, sorry, no, distance is 3, right? Distance is 3. And also, if I sit here, then distance is 3 as well. So no rule is broken. So basically, we can just actually kind of simulate the process, and at each point, just check that is the rule broken or not. And also, so see, the first people, where will they sit? That's the thing. See, like that's the what we need to think about. That let's say n is equal to 9. Okay. So where will the first person sit? Basically, there are no people sitting right now, right? So the rule one is actually primary goal is satisfied for every seat here, because the distance is non-existent for any seat. So he can sit anywhere. But the secondary goal of him is that he will try to sit so that the second person that arrives will get a seat as far as him from possible as possible. So basically he'll try to sit here, that one, so that two can sit here. Two can sit as far as him as possible. So either one can sit here and two can sit here, uh, or it can happen that one sits here and two sits here. All right. So that's what happens. So either one here, two here, or one here and two here. Okay. And then just choose the maximum segment length, or like basically the one with highest value of the ceiling of x by 2. That's what they will do. So basically, let's say we know that the third person comes and sits here. Then we'll check ki, okay, since this 3 is the midpoint of this 2 and 1, therefore the rule is not violated. Okay. Now we have these two segments, 4. Okay, wait, sorry, my bad. Now if this 3 sits here, then the rule is not violated, because this is the midpoint of this 2 and 1. Then let's say 4 comes. This 4 comes here. Okay. Now actually, when this 3 sat, then we have two segments. One segment is this, and the other one is this. Okay. So if suppose 4 sits here, he's in this segment, but this segment center में नहीं है वो, right? He should be at here. If he wants to be in this segment, he should be here. So since 4 sat here, then it is wrong. So basically, we can just simulate this process. We can say we can just check 1 and 2 that they are the endpoints, and then we can just check that 3 is coming. So center में होना चाहिए वो. Then 4 is coming, so he should be at the center also. So at every point, we just check that they are at the center and they are the farthest that they can be. So we can just check that using some sets and lower bound, upper bound. Like it is just implementation now. Like there is no particular heavy logic in this. It is just implementation, how we implement. Okay. So basically, how I implemented this was like, first of all, I created an array where I stored that, okay, where did each person sit? So let's say for example, we were given the input that 2, 1, 4, 3, and 5. So from this, I just created an array that, okay, where did each person sit? So one sat on 2, right? So we have 1, 2, 3, 4, 5 here. Uh, so okay, we know that one sat on 2. then 2 sat on 1, 3 sat on 4, 4 sat on 3, and 5 sat on 5. So actually this is very bad example because the array becomes same. I'll take another example. My bad. 3, 2, 4, 5, 1. Okay. So suppose this is the input. So I'll just make an array of where they sat. 1, 2, 3, 4, 5. So 1 sat on the fifth one, 2 sat on second one, 3 sat on the first one, 4 sat on third one, and 5 sat on fourth one. So this is the array that I have made. And then I'll just traverse through this array, and then I'll just maintain a set of what the indices are already taken, and then I can use lower bound and upper bound to figure out whatever I want to know. So see, this is the first step that I made, that okay, where did the guys sit? Now what I'm actually doing is I'm maintaining a set. What's that set? That set is actually that how which are the indices that have been taken. Like let's say for example in samples, the sample is 143652. Okay, so 143652. So in this case, what I actually did was first I created the inverse array. Like okay, this is called inverse array. Okay, this thing is called inverse array or inverse permutation. So I created the inverse permutation. So 1 is at 1, 2 is at 6, 3 is at 3, 4 is at 2, 5 is at 5, and 6 is at 4. Okay. Now what I did, I just maintained that currently what are the indices. So first of all, 1 will come and sit here. Then 2 will come and sit here at 6, right? Then 3 will come and sit here. Now I want to check that, okay, starting from 3, is he correct? Like, is he bringing any rule or not? So to do that, I'll just check that what is the segment that he is sitting in. So right now there's only one segment, right? This 1 to 2, and this 3 sits here. Now there are like two segments. Now this is one segment and this is one segment. Also, this 3 sat here. So in the set, I have also inserted the 3. So initially it was 1 comma 6 because the positions 1 and 6 were occupied. Now 3 came here and sat at the position 3. So now the set has 1, 6 and 3. So 1, 3 and 6 in sorted order. 1, 3 and 6. Now 4 came and sat at 2. Okay. So now I just use lower bound and upper bound on this set to figure out that where did 4 sit, which segment. So I figured out that he is a segment of 1 comma 3, right? And actually I also have a multiset of the segment lengths. So basically currently there are two segments, right? This one segment is of length 1 and another one, this is of length 2. So I'm also storing a multiset of this current lengths 1. So whenever, let's say initially actually it was 4, okay, so when 3 didn't come here, the set contained the indices 1 comma 6 and the multiset contained the length 4, because there is only one partition of length 4. All right, so now what happens is 3 came and sat at the position number 3. So what happened that this 4 actually broke into 1 and 2, and another index 3 was added to this. So using these two things, like using this multiset and this set, I can actually figure out that is the rule getting broken or not. Basically what I can do is right now it is like this. Okay, now 4 comes and 4 sits here, right? So what I'll actually do is, first of all, I'll check that which segment did 4 sit in. So using this set, I found out that 4 sat in the segment 1 comma 3. So I realized that okay, the length of that segment was 1, this length was 1, 3 minus 1 minus 1. So the length was 1. And if he sat there, then the distance is 1 by 2 ka ceiling, right? So that is 1. So that's what I realized, that 4 sat here at a distance of 1. Now I checked that what was the maximum distance that he could have sat. Like basically he had two options, right? One option he had was to sit here at the index 2, and one of the options that he had was to sit here, like either here or here, basically in this segment. But he chose to sit here, and the distance was 1 in that case, the ceiling of 1 upon 2. So I'll just compare it with the distance that he would have got if he sat here. Like if he had sitten here, then what's the distance that he would have gotten? So let's say if he sat here, then like what is this? This is the longest segment. Like basically, I just checked that if he sat in the longest segment, then the distance would be what? So the longest segment is through this is 2. Like I have multiset, right? So I know that the longest segment is 2 right now. So I'll just check that if he had sit in this 2, then what's the distance? Then the distance is still 1. So right now he sat here and the distance was 1, and the maximum distance that he could have sat is also 1. So that means that the rule is not broken, right? So that's how I check for this 4. So now I just place this 4. I just place this 4 right here, and I update the multiset and the set. Like I insert the element 2, I insert the index 2, and also I break this 1 into 0 and 0. So right now it contains 0, 0, and 2, the multiset. So that's what I am doing. I am just keeping track of the indices and the segment lengths. And at each step, I'm ensuring that there is no rule broken. Like first of all, I'm ensuring that it is at the middle, at the center, right? And if it is at the center, then I'm ensuring that it is at the minimum distance, or sorry, the maximum distance that it can be, by comparing it with the maximum of the multiset. Okay, so that's what I am doing. So I hope the logic is clear. If the logic is clear, then please give me a yes in the chat. Clear? Okay, yes. Good. So I'll show you the code. Basically, this is just implementation. Like, um, there is no real logic here. Okay. So yeah, first of all, I take the input IAP command, and if n is equal to 1 or n equal to 2, then I just print yes. That is some edge case handling that I'm doing. Then for int I equal to 0, I less than I plus plus, I decremented pi. Actually, I did this so that the permutation is from 0 to n minus 1. So it is easy for me to handle. And then I create this inverse permutation. Inverse is that this permutation, that where is everyone sitting? This inverse permutation. Okay. So that's how you create this inverse permutation, that IP of P of I is equal to I. Like P of I is sitting at ith position. That's what it means, right? Now, if P0 equal to 0 and Pn minus 1 equal to 1, that means that in the starting we have 0, like in the input. In the starting we have 1 or 0 in 0 indexing, and in the end we have 2 or 1, then that is fine. Or if in the starting we have 1 and in the ending we have 0, then it is also fine. So that's what I check first, and in the else I just print no. Okay. But if that is the case, then I am just handling, like I am just making all of these sets and multisets. So this multiset ms and this set of indices. Okay. So indices dot insert 0 and n minus 1. So basically I have already placed 0 and 1 at the index 0 and at the index n minus 1, and ms dot insert n minus 2. So n minus 2 is like the gap, right? The initial gap. We have only one gap initially, right? So here we have a person and here we have a person. So this initial gap is n minus 2, right? Now I just iterate from 2 to n, and the IP of I is that index that the current person is going to sit on. So I found the lower bound. I found the lower bound in the index. Like in the index set, I found the lower bound of the current index that the person is set, the person came. So let's say 3 came here. Then I am finding the lower bound, like 3 came on the index 3, and the indices we have in the set is 1 comma 6. So the lower bound of 3, which is 6, I am finding that. So it is equal to lower bound, and a is equal to star it, that means the 6, and b is equal to star previous it, so that means the 1. So basically the current index is in the segment b comma a, right? If func of b a minus b minus 1, this func is just x by 2 ka ceiling. Okay, like I have defined it right here, return n minus 1 by 2. Actually this should be n plus 1 by 2, but it doesn't really matter because I am just checking inequalities. So this one also works, but it should be n plus 1 by 2. So okay, if func of a minus b minus 1, that is the distance, the current distance, is not equal to func of star ms dot r begin, that is the maximum distance, that is the maximum gap that we could have achieved. Like if it is not equal to that, if it is less than that, then just print no. Okay, like basically he selected the wrong segment to sit on. So let's say for example, if we have something like this, now let's say 4 came and 4 chose this segment to be, then that is wrong because this segment has definitely more distance, right? So that's why I just print no here. Now so okay, now if this is true, like if I don't return from here, then that means that the person has selected a correct segment. Like it is possible for him to sit in the center of that segment and basically like maximize the distance. So if I reach here, if I reach on this line, then that means he is on the correct segment. But now I just need to verify that he is at the center, like he should at the center. I haven't checked that right now, so now I'll check that is he at the center or not. So for that I have two cases, that is a minus b even or odd. So if a minus b is even, then basically the midpoint of them is a plus b upon 2, and if that is not equal to the current index that he has sitting, then we return no, right? And if a minus b is odd, then there are two midpoints, either a plus b upon 2 or a plus b upon 2 plus 1. So if he is sitting in either two of these points, either one of these points, then we have no problem, and otherwise we return no. Okay, and now we just insert like index dot insert ip of I, and also uh, like basically we update the lengths of the indices. Okay, so let's say 4 comes and sits here. So initially this length was 4, but now someone came here, so it got broken into 2 and 1. All right, so a minus b minus 1 it was initially, but now uh, got broken into ip minus b minus 1 and a minus ip minus 1. All right, so that's what we will just erase and delete. I'll erase and insert. Okay, so we have this for loop, and we just do this process from 1 till n. from 2 till n. And if it didn't return no, like at any one of these 3 points, if it did not return no, then it means that all of the people have set in and no rule has been broken. So the answer is yes, and we print yes. Okay. What does assert do? Assert basically does that, um, whatever I write in this assert thing, if it is false, then it will throw a runtime error. Okay. Like if it is equal to index.end in this case, like if that happens, then it will throw a runtime error. So actually I added this so that if I submit this code and I get a runtime error, then I would know that maybe this assertion has failed. Like maybe it has somehow become index.end. Like I knew that it can never become index.end. So that's why I just put it here that it is not equal to index.end, because somehow if it is become like somehow if it becomes index.end, like if I have made a mistake, then I will know because I will get runtime error. Okay, that's what assert does. All right. Okay, so if it is clear to all, I will move on to the next one. Cool checker. Okay, so this problem is pretty nice. um okay, let's do this one first. So this was the problem, right? The cool subsequences. Now actually we are supposed to write its checker. That is the answer printed, uh, like correct or not. Okay. So basically you are given two arrays A and B of lengths n and m respectively. A non-empty subsequence S of the array A is said to be legal if average of S belongs to B. Okay, where average of S is the average of the elements of S and equals the sum of elements, like average. Okay. And rounding is not done when computing the average. For example, the average of 1 to 5 is 8 by 3. Now your task is to find any subsequence of A that is not legal. Okay. So basically we have two arrays A and B of lengths n and m respectively, and we have to find a subsequence of A such that the average of A, like average of the subsequence does not lie in B. If there are multiple subsequences that are not legal, you can find any of them. Okay, so this is the question, that we have been given an array A and we have to find any subsequence. We have been given an array A, let's say 1 2 3, and array B is 2 4. Then we need to find any subsequence whose average does not lie in the array B. Okay, so let's say if we take 2 comma 3 as subsequence, 2 comma 3 is subsequence. So if we take that, then the average is 2.5, which does not lie in B. Okay, so that is the question here. And if there are no subsequences that don't have average in B, then we just print -1. If every subsequence is legal, then print -1. Okay, so actually this problem is very interesting because the way that we are solving it is very like non-standard. Okay, so let's think about it. Now let's just take this test case only, that A is 1 2 3 and B is 2 comma 4. Okay, so actually if you can see that if we take 2 comma 3, then the average is 2.5, and without even looking at the array B, we can say that 2.5 does not exist in the array B. Why? Because B only consists of integers, right? B has only integers, and that's why the array A, like The subsequence 2 comma 3 definitely is not good. It is not legal. So that's why we can just print 2 comma 3, right? Or actually what we actually that what we could have done is we could have printed 1 as well, because the average of 1 is 1, and 1 is not in this subsequence, or not in this array B. So we can print 1 as well, or we can print 3 as well, or we can print 1 2 as well, because the average is 1.5, which is not an integer. So that is the possible answers for this test case. But what I am interested in is finding like the decimal ones. Okay, like let's say this 2 comma 3 is here, then we can just print 2 comma 3, because one of them is even and other one of them is odd. So if we have in the array A, if we have the numbers like even and odd, if we have both parities even and odd, then definitely we can say that um that those two numbers are not legal. Like we can just print those two numbers, because their sum divided by 2, that is the average. This is not integer. Okay, so that's what we can do. But what if all of them have the same parity? Like what if all of them are even or all of them are odd? Then actually what we can do is, and then actually what we can say is that all subsequences of length 2 are actually good. Like not good, like, but they are integral. The average is integral, right? At least we can say that if in array A all of the numbers are of same parity, like all of them are odd, let's say, then definitely all subsequences of length 2 have integral average value, like 3 plus 7 by 2, 10 by 2, which is 5. So it is integral, but definitely all of them have integral of length 2. So now what do we do? Let's look at length 3. Okay, so let's say we have this. So 5 plus 7, 12 plus 9, 21. 21 by 3 is 7. So it is integral. But let's say we take 3, 5 and 7. Or um what should we take? Let's say we take 3, 5 and 9. Okay, 3, 5 and 9. This is actually not integral. 17 by 3, which is not integral. So we can print 359. Like without even looking at the array B, we can say that 359 is not a legal subsequence, right? But what if all, even the 3 length ones are also what? Are also integral. Then we look at 4 length ones. So, and that's like, and so on. That's what we can do. So that is one approach that we can follow. But obviously this would give TLE, right? Like even checking 2 length ones will give TLE, because it will take NC2 time. If I want to check all of the 2 length subsequences, it will take NC2 time, which is like n square time, and we cannot take O of n square. So what we can actually do is try to analyze that what is the condition. Okay, so actually what is the condition? Let's think about it. Let's say we have some numbers a1, a2 up to an. Okay, now let's say I select a subsequence of length 2. Okay, so let's say I select a4 and a6. So by 2 it will happen, and I want this to be integer. So it is integer if and only if a4 is odd and a6 is odd, or a4 is even and a6 is even. Actually, more particularly, I want that all of the subsequences of length 2 have integral average. Okay, so what does that mean? That actually every number mod 2 should be the same. Like that is the observation here, that the mod 2 with every number has to be same. Why? Because if it were different, like one was even and one was odd, then you could just take even plus odd, right? So this is for 2. Like basically, we want the modulo 2. We want AI mod 2 equal to same for all I, right? This is one condition. Like if this happens, then we cannot take a subsequence of length 2, right? Now let's say we try length 3. Length 3 we try, okay. So what will happen? It's like AI plus AJ plus AK divided by 3. So what I want is AI plus AJ plus AK should be a multiple of 3, right? So actually in the 2 case, you saw that we wanted that all of them have same modulo with 2, right? Now even in 3 case, we can see the same. We can generalize it that every number should have same modulo with 3, because if it doesn't have the same modulo with 3, then actually we can do something, okay. What we can actually do is, let's say there are some numbers which have modulo with 3. Say modulo with 3 can be 0, 1 or 2, right? So let's say there are some numbers with modulo 0 and some with modulo 1 and some with modulo 2. So what we can just do is take a 1 with 0, take a 1 with 1, and take another 1 with 1 and divide by 3. This won't divide by 3. So like that is the observation. So basically what we want is, we want all of the numbers to be having same modulo with 3. Like if you want the formal proof of that, I can give that as well. So let's say we take AI, AJ and AK, okay. AI, AJ and AK. Now let's say that the modulo of the sum, like this is equal, like this is divisible, suppose this is divisible by 3, okay. Now since there are multiple mods, okay, what I can just do is, suppose this AK is of mod 3 or mod 0, let's say this is 0 mod 3, okay. Then I will just find a number which is not 0 mod 3, like it is either 1 or 2, and I'll replace it with AK. Like basically this I, J and K, let's say it is divisible, then I can just find another AI plus AJ plus let's say AL, where K and AK and AL don't have same mod. So if this is divisible by 3, then definitely this one is not divisible by 3. So therefore we would have our answer as this one. Like if not all the array elements have the same mod with 3, then definitely we can find a subsequence which has non, like which is not divisible by 3, the sum of which is not divisible by 3, okay. So basically we want AI mod 3 to be equal to constant for all I, right? So for length 2 it was AI mod 2 should be same, and for length 3 it is AI mod 3 should be same. So actually what you can say is that, okay, let's say this constant is k1, AI mod 2 is equal to k1, so k1 can be either 0 or 1, and AI mod 3 is equal to k2, so k2 is either 0, 1 or 2. So we want that AI mod 2 is equal to k1 and AI mod 3 is equal to k2. Then actually if you have studied something like Chinese remainder theorem, CRT, then actually these two congruences imply that AI modulo 6. Like the LCM of 2 comma 3, it is determined. Like this AI mod 6 can be determined from these K1, K2 values. Like that is what the Chinese remainder theorem says. Like for example, if I give an example, um, let's say we have AI mod 2 equal to some, let's say 1, and AI mod 3 is equal to, let's say 2. Then what's the number? Then the number is, I guess, 5, right? Because 5 mod 2 is 1 and 5 mod 3 is 2. So number can be either 5, or it can be 11, or it can be 17, or it can be 23. Wait, yeah, 23, and so on. So basically, AI mod 6 is fixed. Like AI mod 6 is determined. Like by these two equations, AI mod 6 is determined, where 6 is the LCM of 2 comma 3, right? So in general, if we have some congruences, like if we want that, okay, AI mod M, suppose AI mod M1 is equal to K1, then AI mod M2 is equal to K2, and up to AI mod MK or ML is equal to KL. Like if these are simultaneous equations, then CRT, Chinese remainder theorem, states that the mod of AI, like AI mod LCM of this M1, M2 up to ML can be determined, right? So basically, let's say we have, let's say, three equations. Okay, so let's say I want AI mod 2 to be equal to 1, then I want AI mod 3 to be equal to, let's say, 2, and AI mod 4 to be equal to, let's say, 3. Okay, then actually the solution to these three equations will be of the form that AI mod LCM. So what is the LCM of 2, 3, and 4? 12. So AI mod 12 will be something. So what is one solution to this? If I just take, like, let's say AI equal to, what shall I take? AI equal to 11. If I take AI equal to 11, then mod 2 is 1, mod 3 is 2, and mod 4 is 3, right? So basically AI mod 12 is equal to 11, or the numbers of the form 12k plus 11. Okay. So all the numbers of this form will satisfy these equations. That's what the Chinese remainder theorem says. And only the numbers of this form, like only these numbers and no other numbers, right? So the LCM of this. Now actually, how can we use this to our advantage? How? What we can actually observe is that, okay, uh, when we are trying for 2, all right, when we are trying for 2, we want AI mod 2 to be some constant K1, or let's say K2. Then we're trying for 3. So AI mod 3 should be equal to K3 for all AI. Then AI mod 4 should be equal to K4, and so on. So if we actually go till, let's say, 18, if we go till AI mod 18, this should be equal to K18. Then actually the solutions. So we have the 17 equations, right? So if we want to solve these 17 equations, then the solution will look like AI mod LCM of 2 to 18 is something like, let's say, X. Like what I want to say is that the solution will look like this. That basically, the modulo of AI with respect to the LCM from 2 to 18 will be some value. And actually, the LCM of 2 to 18 is actually very large. like it is of the order 10 to the power 8. Okay, so let's say this x is equal to 1. Let's say hypothetically x is equal to 1. Then okay, let's say this is L. All right, this AI mod L is equal to x. So one solution is AI equal to 1. Now what is the next solution? Like above, if we see that AI mod 6 is equal to 5, then that means that either 5 or 11 or 17 or 20. So 5 plus 6, 5 plus 2 into 6, 5 plus 3 into 6, and so on, right? So let's say this x is some value, let's say 1. So one solution is AI equal to 1. The other solution is AI equal to L plus 1. But this L is actually very large, 10 to the power 8. So 10 to the L plus 1 is actually a pretty huge number, which is actually the out of the limits of the problem. Like the constraints of this problem are up to 10 to the power 7 only. So my point is that if all the numbers have same modulo, with respect to all of like 2, 3, 4 up to 18, if they have the same modulo, then it is guaranteed that they have same modulo with the LCM. And if they have same modulo with the LCM, since they are up to 10 to the power 7 only, we can say that um, the numbers are all the same, because the number cannot be L plus 1, right? Because the numbers are up to 10 to the power 7 only. It cannot be L plus 1. It can be only 1. Actually, this 1 is just for example. Okay. Like if x was 1, then the answer would be 1, L plus 1 and all. But let's say x was something like 15. Then the answer would be 15, L plus 15, 2L plus 15, and so on. But definitely these numbers cannot be it. So the only possibility is 15. So if all the numbers in the entire array is equal to 15, then only it is possible that um, that they are equal modulo all of these numbers. Okay, so that's what the observation is, that solving these congruences simultaneously blows up the LCM. Like there is only one particular solution of this equation because AI is restricted. All right, so that is actually the solution to this. So actually, but yeah, that is assuming that n is sufficiently large. Like if n is, let's say, just 10, then the equations will only last up till AI mod 5 is equal to k5 and up to 10 only. So actually, in that case, it would be LCM from 2 to 10. So which is not very large. Like LCM of 2 to 10 is not greater than 10 to the power 7. So it is possible that not all the values of AI are same, but their modulo with all of these numbers up to 10 becomes same. Okay. So if n is large enough, then definitely we can say that all AI have to be same. Otherwise, it is not possible that uh, that all of them have same modulo. So basically, we can always find a subsequence which has an average of decimal. Okay. Like basically what I proved right here is that suppose you have an array of length 18. Okay, let's say you have a1, a2 up to a18. Then it is always possible, like, and okay, since all of these AI are less than or equal to 10 raised to the power 7, right? So if all of them are not the same, like if some of them are distinct, like let's say a1 and a18 are not the same, then definitely at least one of these congruences, like uh, we wanted AI mod 2 to be equal, right? Then we wanted AI mod 3 to be equal and AI mod 4 to be equal. So we wanted till AI mod 18 to be equal. But actually, if A1 and A18 are different and both are less than 10 to the power 7, then definitely uh, A1 mod L and A18 mod L both are different, right? where L is the LCM from 2 to 18. So definitely I can say that mod some value, like either A1 mod L, basically either A1 mod 2 and A18 mod 2, or A1 mod 3 and A18 mod 3, or A1 mod 4, A18 mod 4. So either of these equations are not satisfied. So like what I'm trying to say is that if I have an array of length at least 18, or let's say I have an array of length 18, where not all the numbers are distinct, not all the numbers are identical, then we definitely have a subsequence for which the average is not for which the average is not integral. Okay, because all of these congruences cannot be simultaneously solved if AI is less than 10 to the power 7 and they are different. Okay, like there is only one solution to these congruences for AI less than 10 to the power 7, or maybe there is not even one solution. That can also happen. So my point is that solving all of these congruences is actually very particular. So if you go till 18, then you will find only one solution in this range, and therefore if you have two different values of AI, then definitely some congruence is not satisfied. Like modulo some value, they will not be the same, and then like and therefore at least one subsequence is not good, it is not legal. Okay, so that's what I have just proved, that if the length of of a sequence, if n is greater than 18, greater than equal to 18, and if it does not have all same elements, then definitely a legal subsequence, like an illegal subsequence, exists in that. Okay, so what can we just do now? We want to construct a subsequence of that type, right? So to do that, we can just, like, if n is greater than equal to 18, if n is greater than equal to 18, then we can just select some 18 integers from that. Like from that array, we can just select some 18 integers, so such that not all of them are same. Okay, so not all of them should be same, and select 18 of them, and then just apply brute force. Like just iterate over all subsequences of this of this array. So there are at most 2 to the power 18 subsequences. So just iterate over all of them and calculate their sum. You can use DP for that. You can use bitmask DP. Like DP of k will store the sum for the bitmask k. Okay, so you can do that, and like basically iterate over all the subsets of this 18 length array, and check that does that subsequence has a sum that is divisible by I or not. Like if the length of that subsequence is I, then if the sum is not divisible by I, then you can just print that subsequence. Okay, so that's what you will do. And if n is less than 18, then you can just do brute force directly, right? So basically if n is greater than 18, then just select some 18 integers and do brute force on that. And if n is less than 18, then just directly do brute force and it will pass. All right. And also, let's say if n is greater than 18 and all the elements are identical in the array, then so let's say we have something like 2, 2, 2, 2, 2, and like 1,000 times we have 2. Okay. So any subsequence that we select, it will definitely have average equal to 2. So we can just find out that does this average occur in B or not. Like if does 2 occur in B, is there 2 inside B? And if there is not 2 inside B, then we can just print 2. Like we can just print this subsequence. And if there is 2 inside B, then definitely there is no good subsequence. There is no illegal subsequence, because all subsequences have average equal to 2. All right. So yeah, that's what you can do. And like the logic was up to here only. Now I'll show you the code. Okay, so we have, I took the input nm, input a, input b. If n is greater than equal to 18, then set LLS. So what I'm doing is I'm just inserting all of the elements inside the set. Okay. Now if s dot size greater than 1, that means not all elements are same. So I'll first go to the else condition. If all elements are same, then I will check that, okay, does that element occur in B or not? If it occurs in B, then I just print -1, and otherwise I just print the one length subsequence of that. Okay. But now what if there are more than 18 elements and not all of them are distinct? If that is the case, then what we can just do is we can extract any 18 elements which are not equal. Okay. So I have just extracted, suppose I extracted 17 elements. The first 17 elements I pushed back in this temporary array. And then the 18th element, I pushed it such that it is not equal to the rest of them. So if it is not equal to s dot begin, then I just push back and then I break. And basically I just um, transferred the temp array into the A array and set n equals to 18. So in this part, I am just doing that. I am extracting any 18 elements which are not distinct. Sorry, which are not identical, not all identical. And then I here at the bottom, I am just doing that brute force kind of thing. That I am iterating over all the subsets. Like I am having a bitmask DP kind of DP of 1, like 2 to the power n, where DPI stores the sum of ith subset, like ith mask. Okay. So I just iterate over all the subsets in 2 to the power n. And yeah, this is like the whole brute force kind of thing. That what I'm doing is, let's say I want to um, find the answer for I. Like DPI I want to find. So I means the mask I. So first I'll find the last set bit, that is J. And the DP of I is just DP of i's or jth element plus A of J. Okay. So that is my transition. And if the sum, like, and k is the pop count, that is the number of ones, that is the number of elements in the subsequence. So if DPI, that is the sum divided by k, like if the sum mod k is not equal to 0, or s dot find dot, like s dot find sum divided by k, that is the average. If s dot find average is equal to s dot end, like s actually stores the elements in B. Okay. So if the average is not there in B, or the average is not integral, then we can just print that entire subsequence. So I'll print k, and I'll print all of the elements that are in this subsequence. All right. So this is how I iterated over all the subsets. And in the end, I just printed -1. Like if I don't see out here and if I don't return, then I iterated over all the subsets and I did not find anything. So I print -1. Okay. So I hope that is clear. And if it is clear, then we'll end this PCD now. So, okay. All right. So if it is clear to everyone, then I'll end this meeting. And thank you all for watching. So if you are on YouTube and if you have any doubt, then you can just ask in the comment section. And if you have any feedback for me, then also you can just give it in the comment section. And also, like, if you don't know CRT, the Chinese remainder theorem, then actually this problem is quite, like, it is kind of difficult for you. So I think you should um study this Chinese remainder theorem first, and then again try this problem. Okay. So, anyways, I'll now take your leave. Thank you all for watching. Bye bye.